Hi everyone and welcome to the learning curve. In this video I will be looking at optimization. Particularly we'll be using linear programming, which is a common mathematical technique. We're going to be using this technique to decide on the optimal quantity of products to produce in order to maximize profits. Linear programming problems are very common in practical business life to make decisions as to what is the optimal quantity of products which make up a company's fleet or inventory that should be produced in order to maximize profits or minimize costs. So here we are told that Jerome Constantine is trying to determine how many units of two types of dishwashers to produce each day. One of these is a standard model while the other is the deluxe model. Profit per unit on the standard model is US $60 while profit per unit on the deluxe model is US $50. The standard model requires 10 minutes of stamping time while the deluxe model requires 20 minutes of stamping time. The standard model requires 8 minutes of inspection time while the deluxe model requires 5 minutes of inspection time. The company must produce at least 2 standard models and at least 5 deluxe models each day. There are 200 minutes of stamping time and 80 minutes of inspection time available. So when you're setting up a linear programming problem in Excel, which we're going to use Excel Solver to both set up, we're going to use Excel Solver to set up and solve this problem. When you're doing that, you need to set up your spreadsheet in a similar manner to this. So your headings here will be X and Y. X represents our standard model dishwasher, while Y represents our deluxe model dishwasher. If there were more products, you would add more column headings here like Z, P, Q, R, etc. But we only have 2 products in this problem, so we use X and Y. I have this a heading max because it's a maximization problem. The goal of Jerome's Constantine is to determine how many units of deluxe and standard model dishwashers respectively to produce in order to make the highest possible profit, which is max profits. So we have the profit, the heading here, max. We also have headings for constraints because there are a number of limiting factors and requirements that need to be satisfied as part of the production process. So profit can't be maximized indefinitely. It can be maximized subject to particular constraints, limiting factors, or demand requirements that need to be met. So we have to specify the constraints that are outlined in this scenario as well. So we have a heading for constraints, we have a heading for LHS, which means left hand side, and also RHS, which means right hand side. We'll talk more about those shortly. So let us set up the problem based on the information given. So for profit coefficient, we are told that the profit per unit for standard model X is 60 and for deluxe model Y is 50. So we're going to put them here, 60 and 50 respectively. Those are the profit per unit. Next, we're going to place some placeholders where we have solution here. So typically when you're setting up the Excel sheet for these problems, you need solution, you need profit coefficient or cost coefficient depending on the nature of the problem. And you need to list the individual constraints as well. Instead of being specific to the constraints, you could just say constraint 1, constraint 2, constraint 3, and so on. But I am a little bit more specific to the type of constraint in this question. But this is how you would generally set up the framework to enter your data, from which Solver will read to produce the solution that you need. So in the solution row here, which we will need when we're setting up this problem as I indicated, you can leave these cells on the X and Y blank, or you can put a 0, or you can put 1 as placeholder. Either is fine, any of those options are fine. Where you have solutions row here, this is where the solution will appear. When we administer the problem in Excel Solver, the number of units of X to produce will appear here, and the number of units of Y to produce will appear here, and the corresponding maximum profit for those optimal solutions will appear here. Okay. All right, so let's keep going now. On the constraints, we are told that as far as stamping time is concerned, standard model requires 10 minutes of stamping time, while the deluxe model requires 20 minutes of stamping time. So on the X, we're going to put 10 because X is for stamping, is for standard model, and on the Y, we're going to put 20 because Y is for the deluxe model. Right hand side is going to the capacity values will go on the right hand side. So for example, we are told that there are 200 minutes of stamping time available. So we can't exceed 200 minutes of stamping time. So here we're going to put less than or equal to 200 because we can't exceed 200 minutes of stamping time. Now let's look at inspection time. For inspection time here, we are told that the maximum amount of inspection time available is 80. So I can go ahead and insert the 80 there right away and also put the less than or equal to sign here. But let's put in the coefficients of X and Y for inspection time. We are told that the standard model X requires 8 minutes and the deluxe model Y requires 5 minutes. So those are the coefficients for stamping time, inspection time, and we have put in the capacity values here as the constraints, as the right hand side values rather. All right, so that's how we set up the linear constraints for stamping time and inspection time. We are further told in the problem that the company must produce at least 2 standard models and at least 5 deluxe models. So because the company has this minimum demand requirement to satisfy, then I have inserted these as demand 1 and demand 2 constraints. So firstly, the company must produce at least 2 standard models. So we're going to just put a coefficient of 1 here to mean 1 by X, and a coefficient of 1 here, and then we're going to place the capacity values on the right hand side. So here I'm going to put greater than or equal to 2, and here I'm going to put greater than or equal to 5, and I'll explain that some more. Okay, so let's look at this carefully. So essentially what we have here is we are told that the company must produce at least 2 standard models. At least 2 standard models. So since X represents standard models, I just place a coefficient of 1 for X, which means 1X is greater than or equal to 2. That's what this row is really saying. 1X is greater than or equal to 2. No need to populate anything for Y there because we're specific now to the demand constraint for X. And as far as the demand constraint for deluxe models is concerned, there's no need to populate the cell here on the X. So we just put a coefficient of 1 on the Y, and that is like saying 1Y or Y is greater than or equal to 5. So this is how you write these kinds of constraints, where you just have a single capacity value to satisfy, like for example, the company must produce at least 2 standard models and at least 5 deluxe models. This is how you deal with these kinds of situations. At least means that value or more, and so that is why for these constraints I'm using greater than or equal to. Okay, so we have inserted the data that we are supplied with in the question itself. The next thing to do is that I need to write a function here, because remember, the optimal profit from the optimal solution will appear on the max. So I'm going to write a function here, a sum product function. So I'm going to say equal sum and then select the sum product function. And what I'm going to do when I select the sum product function is that I'm going to highlight the solution coefficients on the X and Y here, comma, and then highlight the profit coefficients. Similarly on the X and Y, then I close my bracket. So basically what the sum product function is doing here is that it's multiplying the solution coefficients by the profit coefficients. and then I click enter. All right, now this is not going to be the final answer. You see, these are like pseudo values right now on the max. It's a pseudo value on the max and on the x and y for solution. The entire solution row here is really just setting up the problem so that when Excel solver reads, it knows how to compute the solution and what values to utilize. So that's what we will always do on the max. We write a sum product function multiplying the solution values by the profit or cost values, in this case the profit values, the profit coefficient values. Because when the final result is produced, in order to get this profit figure right here, then the solution values on the x and y, the actual solution values on the x and y, would be multiplied by the profit coefficient to produce this result right here. So we're basically setting up the formula for a solver to utilize. Similarly, on the LHS, what I'm going to do here is that I'm going to multiply those same solution values. So I'm going to write a sum product function again. I'm going to say equals sum product. Then I'm going to highlight the solution values on the x and y, which are the dummies of 1, comma, and I'm going to multiply that by the figures for stamping time on the x and y. Then I'm going to close bracket. Now, because I'm going to be copying this result downwards, what I'm going to do is that I'm going to anchor these values. I'm going to anchor the solution values of 1 and 1, so that when I copy this result downwards, the 1 and 1 on the x and y would multiply by the inspection time values, the demand 1 values, and the demand 2 values as well. So since the cell reference for the solution is B2 and C2, here I'm going to put B $sign. I'm going to put a $sign between B and 2, right? And I'm going to put a $sign between C and 2 here as well. Right. And what we're doing is that we are just seeking to ensure that when we copy the values that are anchored here using the $sign, which are the solution values 1 and 1, are uniformly copied downwards. So it's put a $sign between the letter reference and the number, and also before. So it's $sign B, $sign 2, and $sign C, $sign 2, right? Because again, those are the cell references for the numbers here for solution. We're multiplying those by each of these values on the x and y for the constraints, but we're just writing the formula for stamping time right now. We click enter, and then we're going to copy this downwards by going to the bottom right hand corner and dragging downwards, and I get my results there. So what this has done is that it has ensured that the 1 and the 1, by anchoring using the $sign that I illustrated, and then copying down the 1 and the 1 on the solutions, automatically multiplies by the values on the x and y for inspection time, demand 1 and demand 2 respectively. So that is how we are able to get all of these values. Okay, so now the problem is perfectly set up, and now we are ready to use Excel solver. So to use Excel solver here, you will need to, if you haven't had Excel solver downloaded into Excel, there's a way in which you would do it. You would basically just right click in the space here in the far right corner, then do customize ribbon, and when you do customize ribbon, you select add-ins, and when you select add-ins, you select the option that says solver add-ins, and then click go, and then OK, and then it will automatically appear on the data. So here I click data, solver is already there for me, so that's where you will find solver by clicking data. So now I click solver, and when I click solver here, the first thing I need to specify is to set objective. To set objective, I will go to the cell on the max, because that is where I want my profit figure, my optimal profit figure to appear. So I will go on the max, and here I select the cell on the max, and that is good to go. Since it is a max function, a max problem, ensure that where you have two, max is selected. If it was a min problem, like for example, if we were trying to determine the optimal quantity of products to produce in order to minimize profits, then we would have selected min, but here it's a max problem. Now for by change in variable cells, we will highlight the values for solution under X and Y. That's what we'll put on the by change in variable cells. So I'll click this right here, and then I will just highlight the 1 and 1 on the X and Y and click enter. So we've set the objective, we've defined by change in cells, and now we need to define the constraints, and they are going to appear right here. So to define the constraints, I'm going to click add. And what I'm going to do here is that I'm going to specify for cell reference, I'm going to be specifying the left hand side values, and for constraint, I'm going to be specifying the right hand side values. So starting with the first one, I'm going to click this option right here, click this right here, and select 30, enter. Ensure that the appropriate inequality sign is selected here for the first constraint, which is the stamping time constraint. It is indeed less than or equal to. Then over at constraint, I'm going to select the right hand side value of 200, and then I'm going to click add. This will now allow me to add the second constraint, which is the inspection time constraint. So on the cell reference again, I'm going to click here, select the value on the LHS for inspection time, which is 13. Click enter. Ensure that the appropriate inequality sign is selected here, which is less than or equal to. Then go over to constraint and select the right hand side value that corresponds. Click enter, add again, and on the cell reference, I'm going to again select the left hand side value. I have to ensure the appropriate inequality, which is a greater than or equal to, here is selected, and on the constraint I select the right hand side value. Click enter again, and then add. I'm going to add our final constraint, so we repeat the same process. Here we select the reference value here, 1, select the appropriate inequality, greater than or equal to, and then the constraint value would be the right hand side value of 5. And we've finished all of them. So now that we've finished all four, specifying all four constraints, we click OK. Here they are. If you wanted to change any of them, you can just highlight it and click change. Or if you wanted to delete, you just do the same thing, highlight and delete. Okay, so we have satisfied all the conditions here. We have specified the set objective, we have specified by change in variable cells, and we have specified the constraints, the linear constraints. Now ensure that where you have select solving method, instead of GRG nonlinear, you select simplex LP. That's really important. And once you select simplex LP, which is the method that we're going to use to find the optimal solution, and we're pretty much good to go. There are also what are called non-negativity constraints, which are necessary for linear programming modeling, but that is automatically accommodated here. Make unconstrained variables non-negative. That will always be ticked by default. And now we're all set. Go to the bottom right hand corner of your dialog box and click solve. And here we have our solution popping up. Now we can specify additional reports if you want, such as the answer report and the sensitivity report and the limits report. And the best thing to select over here is keep solver solution and click OK. And my problem is solved. The sensitivity report appears down here. I'll be discussing how to interpret sensitivity reports in another video. The answer report also appears here, and the limits report. But going back to the sheet, I told you from early in the problem that the solutions will appear here. Here are the solutions, guys. So based on this solution here, the company should produce roughly 7 units of Deluxe washers, dishwashers. And since dishwashers cannot be broken down into decimal measurements, number of dishwashers, we can't say 7.2 dishwashers or 5.5 dishwashers. So you're going to just round these up to be safe. You're going to round both of these values up because they have a decimal component. So we'd say the company needs to produce roughly 6 units of standard washers, which is X, and roughly 7 units of roughly 8 units of deluxe washers, which is Y. Because actually going down to 5 and 7 would not achieve the optimal profit. So it would be best to slightly overproduce in each case. So just to make it absolutely clear that the company would need to produce 8 deluxe washers and 6 standard washers in order to achieve its maximum profits. So that is our solution right here. And its maximum profit at these quantities, its maximum profits would be $690. So that's the maximum profit. So we have found the optimal solution here. We have optimized this problem. The optimization result here shows us that the company needs to, using the exact figures here, produce 5.4545 of X and 7.273 of Y. But because we're dealing with a discrete measurement, number of dishwashers, number of standard model and number of deluxe model dishwashers, these can't be broken down into decimal measurements. So we'll just round both of these decimal figures up. So producing 6 units of X and 8 units of Y would ensure that the company maximizes its profits. So that is how we'll do this. And this is how we carry out optimization using linear programming, which is an awesome technique that every company should know how to utilize as part of their routine operations so that they are able to determine the optimal quantity of products to produce in order to maximize their profits. I hope you found this lesson to be simple, straightforward, and easy to understand. Remember to like, share, and subscribe as we continue our discourse and indulgence in the world of the mathematical sciences. I will be doing future videos on linear programming and optimization theory, where I will look at how to interpret the sensitivity report as well as the answer and limits report. Thank you. See you soon.